Hi, I'm Corin, CEO and co-founder of Rowan, and in this video we're going to talk about redox potentials. The redox potential of a molecule indicates how easy or difficult it is to add or remove electrons. So redox is a portmanteau of reduction and oxidation. Reduction refers to adding extra electrons to a system, whereas oxidation refers to taking electrons away from a system. And we can actually quantify how easy or difficult each of these half reactions will be in volts. Those are the reduction and oxidation potentials for our molecule. Now, these values can be measured experimentally, but prospectively, if you're considering whether or not to run a reaction or trying to understand what the trends along substrates might be, it's pretty common to look up the reduction or oxidation potentials for a given molecule in a table such as this. So this is a very famous paper. There's other papers like this. And what this essentially does is record sort of a compendium of measured redox potentials for different organic molecules. So we can see here the different oxidation potentials for various aromatic hydrocarbons. These are for alkenes, these are for phenols, and we can see that, adding electron donating groups makes these, voltages lower, making the molecules easier to oxidize, whereas adding electron withdrawing groups makes them more difficult to oxidize, leading to a sort of larger oxidation potential. And this is very nice if the substrates we care about are actually located within this table. But if we were evaluating different substituents, different classes of compounds for which reference data did not exist, we might want to be able to compute the values from scratch for our compound, rather than just guessing what the effect of these substitutions might be. And this is where Rowan comes into play. So from the home screen of Rowan, we can click on this new redox potential prediction button and simply go here and input the structure we care about. So in this case, we can look at phenol because it's a simple molecule and we actually have the reference value on hand. So we'll go add fragment from library. We'll draw a ring. We'll go to the periodic table menu. We'll select an oxygen and put it here. Now this looks like a pretty good geometry for phenol. We might want this OH to actually be in plane, but that's okay. We'll run an optimization as a part of this workflow anyway. So we'll say save. We'll say phenol redox potential. And now here we can choose whether we want to study the reduction, the oxidation, or both. And here we'll just study the oxidation because that's the reference data we have. Okay, and we can now select the mode. So the mode lets us choose, what sort of calculation we want to run. We can tune this, from reckless up to meticulous, as with all workflows in Rowan. But here we'll just leave it on rapid for the sake of this video, and that's a good default for most use cases. And we'll say submit redox. So what's happening behind the scenes while this runs? What Rowan is going to do is first run an optimization on the input molecule, then run a more accurate single point at a different level of theory, here R2scan3c, and then Rowan will add or remove electrons to generate an open shell species that's reduced or oxidized, again run an optimization, and then a more accurate single point on that structure. And so in the end, we'll get a difference in energies between the neutral and the oxidized structure, and that difference in energies can then be converted to the same value you'd measure experimentally against a reference electrode. So it's not exactly just the difference in energies. We have to adjust it linearly by adding a constant to correct for the reference electrode we care about. And in Rowan, all of these values are done, for now, against the saturated calomel electrode, which is standard in the organic literature, and using acetonitrile as the solvent, which is also standard. So I've just skipped ahead to where this calculation finished. And if we look at the runtime, we can see that was only 2 minutes. So it's not long. There's no, crazy deceptive video editing here. I just didn't want to stare at a blank screen for 2 minutes. And we can now see that we have the output of this redox potential calculation. And we can see the oxidation potential here is predicted to be 1.63 volts versus SCE in acetonitrile, just like we discussed. And here, if we compare to the reference value, we can see actually this is exactly right. So we won't always get exactly the right answer here. Unfortunately, our software is not perfect, and these calculations are not perfect. But nevertheless, redox potentials, I think, are, for organic molecules, relatively easy to do a pretty good job at, versus things like pKa, which are a little bit more challenging. So if we look here, we can do a couple interesting things in this calculation. So we can change the reference electrode here to align with different different experimental setups that you might have if you're trying to benchmark this relative to experimental data from your own lab. This is the neutral structure here, and we can also view the oxidized structure, which now, interestingly, is planar. So neutral and oxidized. There's pretty minute differences here. In other cases, there's sort of larger structural changes. We can look and see that these bond lengths do change a little bit between these structures, but it's not a huge change. These are pretty subtle differences. And if we want, we can even go and view the underlying calculation to see sort of what's going on here. Although that's, not typically super helpful.